In this video, we're going to look at a real example to unlock your intuition about how useful AI can be in your engineering career. We'll also look at the hype and some of the reasons why people get put off learning this immensely valuable skill set. In case you're wondering who I am, I'm a professional aerospace engineer. I specialize in applying AI and data science to help us solve problems that traditional methods can't solve. I'm here to unlock your engineering potential by demystifying new technologies and looking at practical applications. In part 1 of this series, we're going to look at a real-world example, a crossover of physics and data, to bridge the gap between traditional methods and machine learning. We'll discuss its implications on an engineering career, then look ahead to what's planned for part 2. As the video goes on, if you're finding it valuable, a like would really help my channel grow. It seems like everywhere you look in tech media, AI systems are pushing further and further ahead at a blinding pace, solving problem after problem. This field can often look intimidating, and while these things are true, a huge gulf is being left behind, as AI can be used to solve very plain yet important engineering tasks. This is what I do for a living. I search my discipline for problems that are solvable by AI, and I massively reduce the work required by traditional engineering teams. Before we get into the example, we need to briefly talk about our evolution and dimensionality. We've evolved to be able to perceive 3 spatial and a single temporal dimension. Whether or not there are more, the important fact is that those are all we can perceive. We use these to great effect when analysing information. By visualising in as many dimensions as possible, we gain an intuition for how changes in the input parameters affect the outcome. This is called abstracting trends, and is obviously common practice in engineering. Even though we can't visualise higher, it is possible for us to abstract higher trends over time. If you saw a million examples of something over a 30-year career, you'd have a pretty good intuition for what to expect, even if it had a lot of moving parameters. Let's look at a very basic example. Imagine we drop a ball from 1,000 meters in the air. Newtonian physics gives us some very simple equations, but we're interested in its true speed, the speed it will be at even with air resistance and accounting for its drop in altitude. If you're an engineer, you'll know eventually the air resistance, or drag, will be equal to gravity's pull, and the ball won't be able to fall any faster. This is known as terminal velocity and is given by this simple equation. What if we want to know the velocity at any point though? Regardless of terminal velocity, what if I just want to know what speed it's going after 5 seconds? This more complex equation can give us the answer there. So let's compute the result. As you'd expect, the ball speeds up and eventually the drag starts to increase to the point where the terminal velocity is reached. This trend is trivial for us to abstract. If someone showed you the beginning and the end of this graph, you'd be able to fill in the rest yourself. Let's say we want to vary the diameter. Simple enough, we just compute again but put a few different diameter values in there. Again, this trend is trivial for a human to understand. But let's just push things out into 3D to make it easier. There. Now we have a really clear view of a 2D trend, and again, any of us could fill in most of the places of this surface if they were removed. What if we wanted to vary mass and diameter? Well, we've used up all our spatial dimensions already. We used up 2 for time and diameter, and the 3rd for showing the outcome. We can, however, use our temporal dimension, time, to plot a 3rd parameter. By animating this plot, you can use time to show how this surface varies as we change the mass. We may need to look at it a few times, but eventually you understand what's going on. Don't underestimate the implication of what we just did. We just abstracted a trend of how 3 variables changing at once influence the outcome of our problem. Now, what if we also wanted to vary altitude and the drag coefficient? All of a sudden, the dimensionality of the problem has increased and we've got no more dimensions to visualize with. This is only 5 dimensions. Imagine testing a vehicle. Different tyres, different diameter wheels, different engine specs, different steering sensitivities, different aerodynamic properties. Then the output dimensions, speed, handling, acceleration, stability. You could collect data on millions of vehicles, but only be able to look at them on an individual basis because across all of them there are too many parameters for you to deal with. This is, in my opinion, the true untapped potential of AI in engineering. It's the abstraction of high-dimensional trends. So, I made a dataset using the velocity equation, which consists of thousands of trajectories of different starting conditions. This dataset is available for free for you to download from the link in the description. We won't go into technical AI programming in this session, but I went ahead and trained a neural network on this data. Now you may be thinking, Why would you possibly need a neural network when we've got the equation? This example is just to show you how a neural net can learn something we already know the answer to, so that we can compare its performance to ground truth. Of course, you don't need this dataset to get started in AI. There are plenty of free datasets available at kaggle.com/datasets. An important thing to know about neural networks: you can train it on all the data you want, but you need to be sure that it can predict new scenarios, otherwise there's no point in having it. For that reason, you keep 5 to 20% of the data aside as a validation set that it never sees during training, so we know it's generalizing trends and not just memorizing. This is the outcome of my neural network's prediction on the validation set. So again, this is data that was never seen during training. We're predicting entirely new scenarios. As you can see, the real and predicted values are pretty much identical. We have a couple of anomalous points in the bottom left. As I said, an AI is never a better method than a perfect equation, but I regularly get performance this good on complex, high-dimensional datasets. There's a saying in this field: everything is an interpolation problem if you have enough data. We may have a ceiling of 4 or 5 dimensions, but neural networks don't have this ceiling. They can abstract trends in n dimensions just by seeing enough examples, and this allows you to leverage these trends to make much better predictions of cases that weren't part of your data. If they have a good data volume and they're applied to the right kind of problem, which we'll discuss in a future video, they will outperform traditional interpolators in prediction speed, memory size, and accuracy. Most importantly, their ability to outperform traditional methods goes up as the dimensionality of the problem goes up. Looking ahead to part 2 of this series, we're going to explore the prerequisites for getting started in AI. How good at maths do you need to be? What kind of programming is involved? And how accessible is it if you're new? What kind of hardware can you get away with? We'll set up a Windows AI environment from scratch, then look at some recommendations for tutorials and online resources. Thanks very much for watching. My channel is new, so if you found any value here, I'd appreciate a like. And of course, if this series sounds interesting to you, subscribe to be notified of part 2.